Let us do another example. The first one was example 1, which was on horizontal. Now we do example 2, which is on the slope. But before I start to explain the question to you, what I want you to do is, I just want to remind you about what happened on the slope, the forces. Right, remember the normal on the slope is in line with the FG perpendicular. And then there is your FG, which is the same as S in our diagram. So if I write the force that is in line with R will be the FG perpendicular. That is weight perpendicular. Now, when this FG parallel is always going down, always, irrespective of whether the box is going down or the box is going up, FG parallel is going down. But let's suppose this was going up. The applied force was this one. And then we'll have to have applied the FG parallel and of course, maybe the frictional force. Sometimes they will tell you whether they give frictional or not. But in the case of our diagram, we have R, which is the same as normal, which is the one which is not going to do any work because of the 90 degrees theta, which is 0. Number 2, S is the same as our FG, and then T, in this case, because the box in this case is going down, T is the same as the frictional force. So I hope you still remember all what is happening here. But let me remind you something again. If I want the F net, if this is moving in the constant velocity, will be F applied, which is going up, minus FG parallel, minus frictional force. Why these two are minus is because this thing is going up, which is positive on the direction of the motion. Remember, every time going on the direction of motion is positive. Whatever is opposite to that is negative. But this, if I put it nicely to you, I will write it like this. What does this mean? It means FG parallel and frictional force are going in the same direction. That's why it's plus. But they are opposite to the applied force. That is what is happening. But remember, the FG parallel is the same as mg sine theta. Why? I can show you that on the diagram. If you take this diagram, you put this line here. Right, this will be your FG again, which is this line. This is parallel to the slope, which is FG parallel. And this is your 90, this is your theta. What happened is, if I want sine theta here, I'll have opposite over hypotenuse, which is FG parallel over FG. Remember, sine is opposite over hypotenuse. Therefore, I'm taking FG to this side. So you have FG parallel. Therefore, wherever I see FG parallel, I put FG sine theta. But what is FG? It's the same as weight, which is the same as mg. Remember that. FG is equal to weight, which is equal to mg. That's why wherever I see FG parallel, I put mg sine theta. You did this in grade 11, you must remember it. Now continuing to do second example. After I've explained to you how does those forces work, let's look at this scenario, which is on the board. The first thing is you are given the crate, which has got a mass of 70 kilogram, and then it's sloping at 20 degrees Celsius on horizontal, and you are given the crate with three forces, R, which is the normal, S, which is the weight, and T is the frictional force. Why? Because the box is going down. And then you are given frictional force of 190 Newton. So we're given frictional force 190 Newton, we're given mass 70 kilogram, and we're given angle, and we're given the distance between A and B, which is 12 meters. Now we can go and answer our questions. Let us do 1.1. So in 1.1, we want a net work done on the object. So I was saying the formula of net work done can be W applied plus W frictional plus WG parallel plus W normal force. Or you can have the W net equal to delta EK. This one is not on the formula sheet, you have to know it. But this one is on the formula sheet. But what we have now in 1.1 is, we have frictional force, so this will apply. We have the WG parallel, so the normal is 0, we don't have to apply force. Therefore, we're going to apply these two in order to find the W net. Right, let's do it. So W net equal to F frictional force delta X cos theta plus FG parallel delta X sine cos theta. Sorry, cos theta here. Right, what is happening here is the frictional force is given as 190, and then the delta X is given as 12, and then remember friction is the opposite force, so it must be 180, which is negative. Plus, remember Fg, this is the same as mg sine theta. The whole of this is only Fg parallel, delta X cos theta. Let's substitute this one. The mass is 70 kilogram. The G is 9,8, sine 20 degrees, and then 12, and then cos 0 degrees, because it was going on the direction of the motion. And then, right, the answer for this is 2851,15, and this one is minus 2280,0J. So when you subtract the two, the final answer is 535,51J. This is our W net. Now in 1.2, they wanted to calculate, they say use work energy theorem. This is our work energy theorem. Remember, this is what we proved this morning, work energy theorem. Right, in our work energy theorem, remember our delta EK, let me write it this side. Delta EK is half mv squared final minus half mv squared R. You remember this. And then our W net, we found it here. We just substitute 535,51 equal to half, and then our mass is 70, and then we want V final minus half, 70, and then this was 0 because it started from rest. So it's 0 squared. Therefore, our V final will be 4,39. Now remember, when you do this, you're going to halve 70, you get 35. 535,51 divided by 35, and then you square root because it's V squared, and then you'll get 4,39 meter per second.